Hi, everyone. Before we get started, I just wanted to let you know about a couple of opportunities that are coming up, and I'm going to put some details in the Zoom chat here. So I've been asked by the Science Student Engagement team to promote these events and opportunities that are coming up. So the first link is about the exam success in 15 minutes or less meetings, which is one of the things that you can count as an event for participation to earn Sci 113 course marks. And the other is that they are recruiting volunteers who would be interested in helping out with first-year orientations next September. So if you follow the links, then you can find out more about both of these opportunities. That's everything from me, though, so I'm just going to hand it over to Marcia to introduce our speaker.
Great, thank you, Caitlin. Welcome, everyone. Welcome back to our fifth lecture this term as part of the Sci 113 Science and Society speaker series. Hopefully you all are enjoying this nice sunny day, sunny afternoon. Just a couple of announcements before I have the pleasure of introducing today's speaker. For those joining live, I'll just let you know that we will be wrapping up today's seminar a little bit early today compared to previous seminars around 1:35. But as always, we will reserve time before we wrap up for your questions and answers, and we'll do our best to address each question. So at that time, once our speaker has wrapped up their talk, you'll be invited to ask your questions in the chat, or please feel free to raise your hand in the Zoom as well. And just as a reminder, as always, that this is an academic setting, and to ensure that your questions and comments remain respectful. As always, you want to be prepared to debrief the seminar in class next week, and the associated worksheet for the speaker series is due at 10 p.m. on Saturday. Okay. With that, it's my absolute pleasure to introduce our speaker for today's lecture, Dr. Agostinos Christiadi. Dr. Christiadi is actually joining us today from Toronto, where he is a postdoctoral researcher at the Vector Institute, and he collaborates with scientists here at UBC. He earned his PhD from the University of Tübingen in Germany, where his work was recognized with the Best Thesis Award. So very excellent work. His research focuses on probabilistic approaches to large-scale neural networks and decision-making under uncertainty. So very pertinent to our conversations in Sci 113. Particularly with applications in chemistry as well as other scientific disciplines, so very interdisciplinary as well. His work's been featured prominently at major international machine learning conferences, and Dr. Christiani is also passionate about mentoring underrepresented students and contributing to the open source community in science. So please join me in welcoming Dr. Christiani. I'm really excited to have you here and look forward to hearing about your work.
Thank you so much, Marcia, for the kind introduction. So today I'm going to talk about my research and how can I situate my research in a broader picture, in a broader picture of this for the society and then for the world. As Marcia said, the talk unfortunately has to end early, but I deliberately only have a few slides, but it's packed with information. And so if you have any questions at all, please just raise your hand. Just interrupt me. I would like this talk to be more like a discussion. But if you want to ask after the talk, that's also fine. Just be mindful that I have a bit, limited time compared as usual. Okay, so the title of this talk is Probabilistic Decision Making, Algorithms for a Better World. All right, so I will talk about a high level explanation of my research on why algorithms for decision making under probabilistic models can be useful for the society and for the world. But first, who am I? Just to give you my background, just to tell a story about where I'm from and how I ended up here in Toronto at Vector Institute. I originally was from Indonesia. It's actually in the middle of the island of Java. So if you heard about Java beans. That's basically referring to the islands. Yeah, it is called Yogyakarta, and it's essentially the cultural center of the Javanese culture in Indonesia, right? So if you want to, see some authentic culture in Indonesia, definitely go to Yogyakarta. Don't just go to, Bali, because that's a bit too cliche, so to say. So yeah, just think about it when you go to Southeast Asia next time. Yeah, I studied software engineering. So my background for my bachelor study was quite, applied. So a lot of coding, writing codes and writing tests and, a lot of programming, so to say. But then I moved to Germany. I moved to the town, or actually a city called Bonn. And Bonn is actually, or was actually a capital city of Germany when it was split into two in West Germany and East Germany. So Bonn was the capital city of West German side. So I studied theoretical computer science. So it's like a switcheroo between, my first background was in software engineering, which is super applied, and then I studied theoretical computer science. So I have backgrounds on both sides, so to say. And this is the building of the University of Bonn, and actually this is one of the most iconic place in the city. And then I moved to the southwestern part of Germany. It's called Tübingen. It's a very small town. It's like 90,000 people. And 2/3 of these 90,000 people are actually students, right? So it's very small, and it's actually a student town. And it's actually the center of machine learning in Germany, if not in Europe. So if you are interested in studying, have a PhD, for example, to study PhD, then Tübingen is actually a very, very nice place to be. And now I'm currently in Toronto. I'm currently a postdoc at the Vector Institute. So Vector Institute is essentially a research organization that specializes in deep learning. So deep neural networks, foundation models, LLMs, and so on and so forth. And it's like one of the three deep learning research institution here in Canada. One is in Alberta, in Edmonton, called AMI. And then the other one would be in Montreal, called Mila. And the last one is Vector Institute. And postdoc here means that I finished my PhD, but I continue in academia, in academic world, not going to industry and so on. But I'm now a proper researcher because now I have a PhD, and therefore I can do a proper research job as a postdoc. So yeah, that's my background. And what kind of stuff do I actually work on, right? So that's the another questions about me. I study decision making in terms of the algorithm. Decision making is prevalent, right? It's all about our what inside our brain. Our brain makes decisions all the time, but that's for neuroscientists, for psychology, people in the psychology and so on. What I care about is how can we mimic how humans make decisions in algorithms, right? In machine learning systems, in machine learning methods, and why do we care about it? Let's use some motivation here. Everybody has a phone, right? In your phone, there are many different technologies, right? For example, the battery, the screen, the processor, camera, and so on and so forth. Let's take a look at the battery of your phone, right? So each year there's a new phone that promises better or longer battery life and so on and so forth. So what does it mean actually? Well, it means that there's some scientists at Apple or at Samsung or somewhere else, they basically find a new materials to build a new battery technology that has higher energy efficiency or energy density in the sense that you can pack more power in the same cubic footage, the same volume, so to say, right? So it's called materials discovery. So you want to find a new materials. Usually it's represented by a molecule in chemistry, if you heard about it in high school chemistry classes. You find a molecule that maximizes or that's optimal in the sense that it's better than before in terms of whatever property that you want to optimize. In the case of battery, that would be energy density, efficiency, and so on. It could be also for drugs. For drugs, that would be for example the efficacy of the drug. We want to find a new molecule such that if we create a new drug out of it, then this drug will be more effective for the population, for example, right? So that's drug discovery. And then, green energy, you want to create a new materials so that you can create a solar panel out of it. And the solar panel will be able to absorb a lot of sun energy better than before. That's another material discovery, right? So as you might know it from these examples, these are very important questions, right? And this can actually be boiled down into the following questions. So we have a lot of molecules, floating around, so to say, in this universe. But which one should we pick so that we achieve the properties that we are targeting, right? Which one out of these 10 to the 100 distinct molecules, which is very, very vast, the space of all molecules are very, very large. But we need to pick one such that when we create a battery, it becomes better than before, right? Such that when we pick a new molecule and then make a drug out of it, it becomes more effective than before, right? And this is a decision-making problem, right? We want to pick something out of some possibilities. We want to decide which one should we pick next, okay? So a simple way to do so is to test one by one, right? Pick one molecule, create a drug out of it, and then test this drug. And then pick another one, and then test this, and then record the number, the efficacy, for example, and so on and so forth. But of course, this is very time consuming. It's also monetarily expensive because you have to do, you have to manufacture the drug and you have to do some testing, right? It's very expensive and it's both time and monetary. And also in terms of the environment costs, right? To make the drugs or to make the new materials, you use a lot of water, for example, you emit CO2 and so on and so forth, right? All of these are very important for the betterment of the world, but it doesn't make any sense if we create new technology while destroying the planet, right? So we want to find an efficient way to find new materials, find new drug, find new molecules, so that everything is can be, the cost can be tempered. But we don't want to sacrifice the efficacy or the effectiveness of the new materials, right? And meanwhile, we humans make decisions efficiently, right? When we want to make a decision, for example, which university should I go to so that I will be able to maximize my income in the future, for example, right? We don't need, ton upon ton of foods just to make this decision. We make this decision very, very quickly, maybe in the course of a week. But generally speaking, it's much, much cheaper compared to the one that I mentioned before, right? So what's in our brain that makes it efficient, right? Can we taken inspiration from how humans make decisions to aid these molecular discovery problems, right? So let's use a thought experiment to get a sense how we make decision and build a model out of it, all right? So suppose you just wake up in the morning, right? You're still in bed and everything is still dark, let's say, right? You haven't seen the outside yet. And then you're wondering, should I bring an umbrella today or not, right? And this is a decision-making problem, right? Should I bring umbrella or not? Decision, right? So how do you approach this decision-making problem, day-to-day decision-making problem? Well, you might think of yourself, you're still in bed, and then you're basically thinking about past experience, right? Oh, usually it's sunny this time around of the year, right? So maybe I shouldn't bring the umbrella. So notice here, we use usually, probably, maybe. So there is some kind of a degree of certainty of what we predict the state of the world to be, right? And then since you are unsure about it, you pick up your phone, right? And then you check the weather app and it says that it's 80% chance of raining, okay? And it's also, this is not certain, right? Because it's only 80%. So it's not, definitely 100% raining. It's only 80%. So we need to reason about it. If my past experience says that maybe it will be sunny, and then my current observation, my current, the data says that it may be raining, then what should my belief about whether it will be raining to be, right? And then you also have preferences to make matters worse, to make matters more complicated. You have preferences. It doesn't really matter if it's some not so severe rains, because maybe I'll just push through it and then don't bring the umbrella because my umbrella is bulky. I don't want to lug them around, right? So based on these three things, you can make decision. So this is just a simplification, of course, right? We don't know what's inside our brain in a certain way, right? So this is just a model on how we make decision, but this is very close, to how we actually make decision day to day, as you have seen in this example. So let's build a model itself. Like, let's be more formal about it. Like, what is this box and what is the other box and which is which, right? So the first one here is called prior belief. So prior belief can be, decomposed into prior and belief. What does it mean? Belief is your prediction about something, in this case, whether it will be raining or not, with some degree of certainty, right? I believe that I will be able to go home today at 5 o'clock EST. I don't know whether I can do that or not, right? Depending on whether there will be a coworker that asks me about some questions, and then I discuss those questions with them, and then so that I got delayed, right? But I have some prediction about it. Well, maybe I can because my schedule is actually rather free, for example. But I'm not sure. So that's what it means by belief, right? And what about prior? Prior is a Latin word, actually. It means that it's before, right? Prior is before. That's actually the same in English. But before what? Prior belief means your belief about something, the state of the world, or something that is unknown to you, before you have seen an observation, right? And what is the observation? And this is the observation, right? Given that I know from the weather app that it says 80% raining, then my belief about whether it will be sunny or not today will change, right? prior means something, your prediction before you see the observation, and observation is the one that, that updates the prior beliefs, so to say. And if you combine them together by updating them together, combining them together, what you get is a posterior belief. Again, belief is the same, is a prediction about some state that is unknown to you with some degree of certainty. And posterior means that after, right, post. After you have seen the observation, what is your belief about the state of the unknown? Right? After I saw my, the weather app says that's 80% raining, my belief about whether it will be sunny or not today will change. Maybe now I only, 20% certain that it will be sunny, right? And this posterior belief about whether it will be raining or not will be useful to make decision whether I'll bring an umbrella or not, right? And what is this before that? Well, this is the utility function. So it seems to be quite loaded. It's a bit hard to parse. Utility, what does it mean, right? Just think about it as some mechanism to encode your preferences on the action that you might take, okay? So combining together your posterior belief about the state of the unknown that's relevant for the decision that you want to make, and your preferences about your actions, then you can make decision or action, right? So far, is it clear? Or do you have any questions? Okay, I think everybody's clear. That means that I did a good job in terms of explaining this in a high-level way. So I hope everybody now agrees that this is something that we might do in day-to-day manner in terms of making decision, right? And so this is the framework of the so-called Bayesian decision making or Bayesian decision theory, right? Don't read too much on it. It's basically just a way to formalize this very intuitive story. Okay. Okay. Another examples of decision making, right? Now instead of making decision yes or no, bring an umbrella or not, I want to make decisions sequentially under to maximize or to optimize or to obtain a good outcome in the future, right? So the future is unknown, right? For example, I don't know what will happen 5 minutes from now. Maybe there will be a questions, maybe there will be no questions, right? But I might be able to predict if I do a good job in terms of explaining things, then maybe there's no question, right? I can make prediction, but I'm not really sure about it, right? Because that's unknown, right? So I can have beliefs about it, right? And this is basically also the same. I want to go to the campus, try for a class, for example. So this is the outcome that we want to maximize. We want to be dry when we arrive. But arriving at the campus while you are currently still at home, that happens in the future. And that's unknown, right? You can make prediction. Well, if it's sunny, then maybe it will not, I'll be dry all the way, right? But what happens if it's not, right? So the way we make decision is that we can make decisions step by step while taking into account of the future that is unknown, your beliefs about the future, right? For example, you're currently at home, and then there are many different branches of actions that you can take. You can walk 20 minutes to the subway station, you call an Uber, or you go back to your backyard and pick a bike from the bike shed, right? And let's say you go to a subway station, then you have different possible actions again, right? If you go to your bike shed, then you can take different actions that leads you to different state, right? And so on and so forth until you arrive at the office, in the campus, and then you see the true outcome, not just your belief. Because when you arrive at the campus, then nothing is uncertain anymore, right? So you know 100% whether you are try or not, right? For example, if you take the cab, maybe you definitely try. But when you are currently at home, you don't know whether you'll be try or not. You can make prediction, but that's not 100% accurate. So there's uncertainty in there. And this is actually a decision making on a graph structure. So maybe you haven't heard about graph, but this is a structure that you will learn if you are in computer science, even in first term, I think, at least in the first year. So it's decision making that is step by step to obtain the optimal outcome. Okay. And you need to take into account about the future outcome that is unknown simply because they are in the future. Okay. And you combine it with the current observations, right? So for example, if you are at a subway station, I'm not really sure if Vancouver is actually has a subway or not, but let's just assume that it's subway underground, right? So if a priori, if your prior belief says that, well, if I take the train and go to subway station, then I'll be dry maybe 90% of the time because subway station is actually underground and I'm sheltered all the way, right? Probably. But then if the observation changes, for example, if the subway station is actually submerged under the water, then you change your belief about the future, right? Well, in this case, if I take the subway, I will definitely be wet, among other things, right? So you will change your belief about the future. So both your belief about the future that is unknown and the current observations are combined together to make a decision on which action should you take next. Okay. So let's formalize this and don't worry about the equations. It's basically just to expose you to this equation that's basically just summarizing all the things that I mentioned before. So you see that there is nothing scary about it. So first and foremost is probabilistic inference. Probabilistic inference is essentially is a mechanism to combine, a mathematical mechanism to combine your observation and your prior belief, right? This is a mathematical way to obtain the posterior, okay? And then when you make decision, you have a utility function, right? So this is the one that encodes your preferences about your action, given your belief about the state of the unknown. And then you make decision that maximizes this expected utility function, so to say. So the best action that you take, the best decision that you should take is the one that's agree with your belief and agree with your preferences. That's basically what it is, right? And later we will see brief examples in materials and drug discovery. And the second part, the second example that I mentioned, that I show you, it was about planning, right? It's decision making step by step to obtain the desirable future, okay? So it's also based on your belief about the future, and it also depends on the current observation about the state of the world that you're currently in, right? And you combine them together so that you can pick the path that you believe leads to the best outcome in the future. And later, I will show you how can we use this idea to make text generations in large language models more efficient. So we reduce the cost of computation that's all these LLMs are using, so that we be more efficient. We can be more efficient, and we don't, destroy the planet, so to say, just to generate text, right? Okay, before I move on to the first part of this diagram, is there any questions? Nope. Okay. If you have any question and you're a bit shy about it, then please just write in the chat, and I will pause and check the chat. Awesome. Okay, so here I will show you the high level of my work, my recent work that is published in ICML, which is one of the flagship conference in machine learning, and it's especially about using LLMs to make decision in materials discovery, right? To find better materials. And this is actually also a collaboration with Jeff Pleiss, who is a professor there or here, depending on where you are, at UBC. Okay, so material discovery, let's make it more formal, right? To see how can you mathematically model this problem. Remember that you want to pick a molecule that maximizes, or to find the one that has better property, right? The property here can be seen as a function of such molecule f of x, right? And think about it this way. So you have a list of molecules, right? So these molecules, using some string representation of these molecules, you have a lot of these molecules, but you don't know the properties, right? So you haven't seen anything, so you have to rely on your prior belief, right? If I know what is these properties for each of the molecule, then I know which one is the maximum. But the fact that I don't know, it makes this problem hard. So remember, when you make decision, you have a prior belief about the unknown, right? The unknown here, the properties, values of the molecules, and you gather observations, right? Observation here means that you pick a molecule, let's say 5 molecules, and then you go to the laboratory and you do some experiment, and then you find out that, oh, it's actually this number, whatever it means, right? And using this observation and your prior belief about the unknown properties, you get the posterior belief using the probabilistic inference framework that I have shown you before. And this way, we can use our belief about these molecules to make decision. Which molecule should I pick next, right? Depending on my belief and my preferences. And then this next molecule can be you can bring this to the laboratory, and then you do experiment, and then again you obtain this property, right? And then you put this back into the observation, and then again and again you make decision sequentially like this, right? So you see that the examples before is actually applicable in this kind of process. So this is the so-called Bayesian optimization, because we want to optimize a function value, and we want to do this in a Bayesian way. Bayesian means using beliefs, right? Using the language of beliefs. And notice here is that not only do we want to find a molecule with highest, or the optimal value of f of x, the property, but also we want to find this in without too many tries, right? If I can just compute everything in this list, then yeah, it's very expensive, right? So we want to reduce the number of iteration, the number of loop of this circle, of this process. We want to minimize the number of such loops, okay? So remember that when you make decision, you can make decision well based on your preferences and your beliefs about the state of the world, right? If you have a belief that is false, you believe about something that is wrong, and yet you believe about it in a very confident manner, we are very, very confident about something that is categorically false, let's say, then you make bad decision, right? For example, I believe, don't quote me, okay? Don't clip this recording. I believe that it's okay to rob a bank. I believe so with 100% confidence, right? So my action will reflect that. I will, after this talk, I will go to the bank and do bad things, right? So that shows you that having good beliefs in the sense that something that reflects the reality is very important for decision making. And what would be the reality for material discovery? Well, it's the reality about the true value of the property that we are targeting, right? If we have accurate beliefs, then we can make decision efficiently because it's very accurate, and therefore our picks, our choice of molecules will tend to be the good ones, right? Makes sense, right? And how can we leverage machine learning models to express such beliefs? Well, can we use LLMs, large language models? They are, seems like an oracle, right? If you go to chatgpt.com and then you ask ChatGPT, and it seems like it knows a lot, right? So maybe it's a good belief for this particular problem. Well, on the other hand, we have this hallucination problem, right? It can show you, wrong answers with very convincing in a very convincing manner, right? LLMs are overconfident. So it doesn't detract from the fact that LLMs can be very, very useful. So the question here is that can we harness the overconfident LLMs for making decision in material discovery? So the way to think about it is that seeing LLMs as they are, not as an oracle, not as like a genie or like some all-knowing being, whatever it is, but as models that has been trained using a lot of text in the internet. And all those texts basically encapsulates or summarizes all the human knowledge, right? So it's like a past knowledge, past experience of humans encoded in LLM. And if you come back to the thought experiments that we had before, then that's basically a prior belief, right? LLMs are prior beliefs. Okay, that makes sense, right? So the question would be, how can we get the posterior, right? How can we do that? Because you heard about it, LLMs are, 700 billion parameters, 1 trillion parameters, or whatever it is, right? So it seems like computationally speaking, we cannot do this. I just want to mention something that's a bit more technical, but yeah, it is basically just to give you some idea that we can actually do this, and we can use parameter efficient fine tuning or PEFT. Don't worry about this. This is just to show you that it's actually doable. Okay. But the main point here is that we can express our beliefs about the unknown property value of the molecule using LLMs. So it's informed. It is informed by the knowledge that's encoded inside LLM, essentially, right? So this is another technical plot, but I'll tell you the way you see this plot is that notice that in x-axis we have cost, right? The number of iteration or the number of loops that we have undertook in the diagram before. And so we want to minimize this. We want to reduce the cost, right? So towards the left, the better, okay? And then in y-axis, we have the performance in the sense that what is the value of f of x that is the highest so far, right? What is the properties that we have found so far? Because we want to maximize this value, then higher is better, right? So towards the left, towards the top, the curves that looks like more towards the left, more towards the top will be better than the others, right? So that's the simple way of parsing this plot. And as you can see, the dashed one here is basically just the one that doesn't use LM posterior essentially, and the solid curves here would be the one that's that uses the LM posterior. And different colors simply basically just means different LLMs. All right, so that's basically what it says. So the methods that I showed you before using LLMs as to inform our decision making actually makes things better. Better here means that we achieve higher property values and we reduce the cost. That's what it means by better here. All right. So before I go to the next one, is there any question? Okay, so there is a question in the chat. How much are software engineering and machine learning related? So it depends. In machine learning is actually a multidisciplinary field. So in machine learning, there is also different kind of level in terms of different levels of in terms of the practicality, so to say, right? So at the base level, you have a very fundamental machine learning, right? So you just do math, essentially. You never code, you never do software engineering there, right? But on the other extreme, you also have something that's much more practical, right? Like computer vision, that's you build a vision systems, for example. You build LLMs, for example. That's very applied. And there you do software engineering all the time because you need to code and so on. Hopefully that helps. If there is no more questions, let's go to the second part, which is planning. Okay, so this plot is quite well known if you follow this LLM's arena, so to say. This is a measure of performance, right, of LLMs like OpenAI o1, for example, and the cost that it uses per task, right? So you have different tasks, and the score here is average over all these tasks. And the task would be, something that humans can solve in 5 seconds, right? Human can do it very, very well. But LLMs here, they are okay, maybe 88%, maybe that's good, right? But then when you see the x-axis underneath, then this is like $3,000 per task, right? So to solve a problem that a human can solve in 5 minutes, oh no, not even 5 minutes, 5 seconds. For example, like we have this pattern and we have another pattern. Do these patterns match together? That's that kind of question, so to say. As an example, LLMs will need $3,000 just to solve these very simple questions for us humans, right? And It means that LLMs are not efficient, right? And this is only about dollar cost, right? But what about environment cost? What about energy cost, emission, and so on, right? So this is problematic, and we want to reduce this. How do you reduce this? Well, we want to push this dots here towards the left, right? So that's the goal. And how can we do this? I'm not saying that we are successful, but that's the overarching goal. That's something that we want to achieve, right? We should strive to achieve that. Well, remember this decision making that I mentioned to you about the unknown future, current observation, and making decision sequentially based on the future and the observation. Here we implement the idea into a way to generate text and therefore solving problems using LLMs, right? And it's published in a symposium called for approximate Bayesian inference last year. And the idea here is basically to notice that LLMs are actually doing some kind of planning, making decisions sequentially. So to see that, I have this diagram, right? So if you have used ChatGPT before, then you basically put or input a text, right? For example, here, hello, my. And then the LLMs or ChatGPT will provide continuation of this text, right? So for example, the continuation could be, hello, my name is John, nice to meet you. That's good. But maybe, hello, my name are it, which is, what is that? It's gibberish, right? And then here, hello, my name house. It's also meaningless, right? So we want to generate text based on our input that is nice in whatever sense, right? So this is something that we want to achieve, right? But if you are currently at this particular point, the black point there, then the generated text is in the future and therefore unknown, right? So this is basically a planning problem again. And LLMs generate the text one by one word by one word, right? So hello, my, and then the next one would be name, for example. And then given hello, my name, you have are or is, and then we need to pick one, and so on and so forth until you arrive at the end where you can rate your whether your generated text is actually good or not, right? So again, it's a planning problem. You make decisions sequentially at every time step in a bid to arrive at a good solution or good outcome, right? So in this work that I'm not going to go deep into, I'm not even going to talk about the technicalities. This is basically the amalgamation or the realization of the probabilistic planning that we have seen before this one. So basically the same intuition as this one, right? So if we use this to generate text and therefore solving problems using LLMs, this is what happened. This is what happens here is that we have the same plot as before, right? The one that we want to optimize is in y-axis. So the higher, the better. Don't worry about what is that, log, whatever. But higher is better. And then x-axis is all about cost, right? How many times you try, how many decisions that you take, right? You want to minimize this. So to the left is better. So the curves that are towards the left, towards the top, are better than the others. And alt here those two things are our methods, right? The methods that uses the ideas that I have told you about. And as you can see, we are able to find good tags, right, with fewer node expansion, meaning that fewer nodes or fewer iterations, so to say, or just in general less cost. Okay, so this is great because by using our beliefs, right, about the future, we can make more informed decision at the current point of time. And therefore, by doing so, we can make decision efficiently, and we don't need to do too many trials and errors to arrive at a good solution. So that's what it means, right? So I'm going to end the talk at this point, and let's have a chat, questions and answers. But before that, I'm going to summarize. So we have seen that the probabilistic inference is very, very useful to make good decisions, right? If your belief about something that is unknown to you is good, in the sense that you are confident, but you are correct about your prediction, then it will be useful for making decisions. If you apply this to material discovery problem, molecular discovery, or to the planning problems, then it means that you can get better results with fewer steps or with less cost, right? So it's important to have a belief that's calibrated, so to say, that is good, right? I mentioned about accelerating scientific discovery because material discovery, drug discovery is a prominent such prominent examples in scientific discovery. Without this, the progress of finding new battery technology, new whatever materials, whatever drugs that you can think of will be slower and slower, right? And we can use LLMs, large language models, so that we can represent our beliefs in a good way, in the sense that we use all the knowledge of the knowledge that's being encoded in the LLM models, and then we harness this so that we can make decision based on this knowledge, so that when we make decision, we can be more informed and therefore make better judgment about things and leads to better decision. And that's it. Hopefully, you're inspired about it, and you can impact the world and society by, even if you are working in more theoretical fields like machine learning or computer science. And yeah, hopefully you enjoy this presentation. And if you have any questions, feel free. I would like to chat with you. Thank you.
Thank you so much, Augustinus. That was really fascinating. Fantastic. So we'll give it a moment for students in the audience who have their questions. Feel free to either raise your hand in Zoom and we'll address you there, or feel free to type your questions in the chat.
Okay, there's a question in the chat. Let me read it. So thanks for making this understandable for us all. My question is about how you might describe AI research as distinct from AI in industry. You mentioned you were going academic track rather than going to industry. What's the difference in what you do? What you would do in each place, and why did you prefer university track? Yeah, it's good questions. It's like basically a diverging path, so to say, in the career, right? It's all about, all about freedom and all about the time scale. In industry, it's all about the pressing matter that we have currently, right? So for example, in this time scale of 5 years, we want to achieve this, right? So that's the time scale part. And also the freedom, right? So somebody higher up in a company has this vision, and you basically just need to work on fulfilling this vision. So this might not be your own vision, right? But in academia, you have more freedom in the sense that I want to do my own research, however niche it is, right? For example, you want to do some esoteric theoretical work, you can do it as long as you can get funded, right? Also, the time scale part is actually much longer in the sense that it doesn't matter if your research is not that applicable for this, in 5 years in the future, but it might be useful, as when you combine your research with all other people's research, and maybe it will be useful in 100 years from now. That's fine in academia. So it just depends on you. I'm not saying that one is better than the other. You just need to ask yourself which one is more important for you. In industry, it's you can get all the computation power that's necessary for you to build LLMs, for example, right? In that sense, it's also very nice environment because you can impact the world by building an AI model that's people in academic world cannot build, right? So it just depends on you.
Yeah, thank you very much. I'm mindful of your time, but I do want to ask your expert opinion. Like, what might you say to our first year science students sort of using LLMs? And I really loved your visual of how they work with the predictive text. But in terms of, either the cost or being a little bit hesitant about using them, what would you say, what advice would you give to first year science students about engaging in LLMs?
Yeah, that's a tricky one because when I was first year undergrad, I didn't have LLMs. Even Google was still, well, it's already there, but it is kind of hard to find things, right? So yeah, so my suggestion is that as much as possible, you shouldn't use LLMs for your study, right? Try to solve problems. If you have a problem sheets, for example, try to do it by yourself first, and then just imagine LLM doesn't exist, right? Imagine they don't exist, and you just do things manually, so to say. Because if you just ask the LLM whenever you have a problem, then you don't learn anything, right? And ultimately, university schools are actually a place to learn how to learn. It's not about getting a right answer, but to learn how to learn to arrive at a good answer, right? So that's what research is, right? So, and also it's also very useful in life, right? If you are super dependent on LLMs and it's very slippery slope, right? Then it's hard to detach yourself, and then when a new situation arises in the future, you will not be able to uh, do things well, right? So yeah, my suggestion is that try as much as possible, do things by yourself first. You can ask LLMs for validation, but don't use LLMs for as a first call, so to say.
Right. Yeah, no, I appreciate that. And I love that your comment about how universities, you're here to learn how to learn. And I would add, learn how to think. So, and do that problem solving process.
Exactly.
Anthony's got a question in the chat there. And maybe given you're short on time, maybe Anthony's question will be our last one for today.
Okay, thank you so much for being mindful.
Of course.
Yeah, so if LLMs are based on prior beliefs, how do they gain those beliefs? do they get it from data that's provided or programmed before any data is provided? Yeah, so LLMs are essentially being trained using text that are available on the internet, right? That's a fact. So, for example, from Wikipedia articles, for example, or from research papers that are available on the internet, right? And this fact alone means that the weight, or that the model itself actually encodes all the knowledge that we have gathered as humanity so far, because all of those knowledge are actually available on the internet, right? So LLMs essentially compresses this knowledge into the model. And you can think of it as a belief, because what do I mean by belief, right? But what do I mean by prior belief? Well, prior belief is something, our prediction about the state of the world based on our past knowledge or past experience, right? And therefore, you can see the connection. LLMs are trained using past knowledge. Prior beliefs are basically something that encodes your past experience and past knowledge, right? So that's why we can make this this connection. And I might need to say that we need to be careful though, because LLMs are not exactly a prior belief, because remember that it's all about beliefs, right? It's all about degree of certainty of your, your prediction about the state of the unknown, right? In LLMs, you don't have this degree of uncertainty. So LLMs are always confident because of it, right? Leads to hallucination and so on and so forth. And it's still an open question. How can we imbue LLMs with, confidence or uncertainty estimates? And that's exactly the line of research that I'm working on mainly.
Excellent. Yeah, thank you. That's what I was wondering, is like, how do we, I guess, ensure that degree of certainty, and then, will that just make it LLMs more efficient and better and less likely to hallucinate? Yeah, that's so
That's very much
interesting.
an open problem. Yeah.
Absolutely. Oh, well, thank you so much, Augustinus. I really appreciate you joining us today. So, everyone in the room, please join me in thanking Augustinus for a really fascinating and amazing talk for our audience today.
Yeah, thank you very much for having me. Had a great conversation with you. And if you have any questions, you can, send emails. I think Marcia will be able to share the email
Yeah, we
address.
can connect for
Yeah.
sure. And yeah, it was just such a fascinating talk that I'm sure our students will really, really enjoy. So, and
All
for
right.
those of you watching the recording later, yes, thank you as well. So,
Thank you. See
thank
you.
you.